Let's talk about an idea that, and I'm not exaggerating here, literally powers our entire modern world. It all started with one simple question, and the answer sparked a revolution. We're talking about electromagnetic induction.
Okay, so let's start with the big mystery. I want you to picture it. It's the early 1800s. Scientists already knew that an electric current could create a magnetic field, but what about the other way around? Could you take a simple magnet and somehow use it to create a flow of electricity? This was the puzzle that was captivating the greatest minds of the time.
You see, people like Oersted and Ampere had already proven one side of the connection. They showed that if you have moving electric charges, you get a magnetic field. But going the other way, turning magnetism back into electricity, that was a complete unknown. It was this tantalizing possibility that, if true, could change everything.
All right, let's dive into our first section, a shocking question. We're going to set the stage and really dig into the central mystery that scientists were just desperate to solve.
So here's kind of how it all went down. By the early 1800s, one half of the story was understood. But that crucial question, it was just hanging out there. Then, in 1831, an English scientist named Michael Faraday basically decided to tackle it head-on. He was absolutely determined to figure out if magnetism could be the source of electricity.
And now for part 2, Faraday's breakthrough experiments. This is where the real detective work begins. We're going to follow Faraday right into his lab and see exactly how he cracked this case wide open.
You know, you might be picturing some huge, complex machine, right? But nope, Faraday's setup was brilliantly simple. He just had a magnet, a coil of wire, and a galvanometer, which is just a fancy name for a device that can detect teeny tiny electric currents. That's it. The true genius was in how he used them.
So first, Faraday holds the magnet perfectly still, right next to the coil. He's looking at his detector, and nothing. Zip. Nada. The mere presence of a magnetic field did absolutely nothing. But then, and this is the key moment, he moves the magnet toward the coil, and suddenly, bam, the needle jumps. A current is produced.
Now, the really crucial point here is that the current only existed while the magnet was moving. The second he stopped, poof, the current vanished. This was his first major clue. It wasn't the magnet itself, but the motion of the magnet relative to the coil that was creating electricity.
But of course, Faraday didn't stop there. He then pulled the magnet away from the coil. And incredibly, the needle jumped again, but this time in the opposite direction. This revealed another huge piece of the puzzle. The direction of the motion actually controlled the direction of the current.
And the clues just kept piling up. He found that moving the coil instead of the magnet had the exact same effect. If he flipped the magnet's poles, that reversed the current too, and he made two more critical observations. The faster he moved the magnet, the stronger the current became, and the more loops of wire in his coil, the stronger the current. He now had all the pieces he needed. This brings us right to section 3, uncovering the laws of induction. This is the big aha moment, where all those clues come together to reveal one of the most fundamental laws of all of physics.
Now, to understand the big picture, we need this one key concept, magnetic flux. Imagine it as the total amount of magnetic field that's passing through a certain area, like the area inside that coil of wire. This is the unifying idea that explains everything Faraday saw.
And here it is, the core insight. A current wasn't produced by the amount of magnetic flux inside the coil. After all, a stationary magnet created a steady flux and nothing happened. The magic only kicked in when the magnetic flux was changing. Pushing the magnet in increased the flux, pulling it out decreased it. That change is absolutely everything. This insight was formalized as Faraday's first law of induction. It's kind of the qualitative rule. It tells us what happens. It simply says that if you change the magnetic flux in a closed circuit, you will create a voltage. Physicists call it an induced electromotive force, or EMF, which is just the force that pushes the electrons to get flowing. So that brings up the next logical question, right? We know a changing flux creates a current, but how much? How strong is it going to be? This is where Faraday's other experimental clues come right back into play.
And this is Faraday's second law, the quantitative rule, that gives us the numbers. The size of the induced voltage is directly proportional to the rate of change of the magnetic flux. This perfectly explains why moving the magnet faster created a stronger current. A faster motion means a faster change in flux. Simple as that.
And this powerful idea is captured in one beautifully simple equation.
The induced voltage, that's E, is equal to the change in magnetic flux, that's the Greek letter phi, divided by the change in time, t. In simple terms, the faster you change the flux, the bigger the voltage. All of Faraday's experiments, distilled into one elegant expression.
So why does a 19th century physics law matter to us today? Well, in this final section, we'll connect this amazing discovery to the modern world you and I are living in right this second.
See, this isn't just some abstract concept from a textbook. This single discovery fundamentally reshaped human civilization.
And I mean that literally. The principle of electromagnetic induction is the foundation of our entire electrical world.
Just think about it. Every single power plant, whether it's hydro, wind, or nuclear, works by moving magnets past coils of wire to induce a current. The transformers that make our power grid possible, the induction cooktop in your kitchen, even charging your phone wirelessly, it all goes back to Faraday's discovery.
A simple question. Can a magnet create electricity? Led to a discovery that lit up the entire planet. It's a powerful reminder that the greatest revolutions often begin with simple, persistent curiosity. Which kind of makes you wonder, doesn't it? What simple question will change the world next?